In this presentation, we're going to look at the Strut-and-Tie method, which is used for deep beam or disturbed regions. By the end of this section, you should be able to differentiate between B and D regions, list and describe the different components of a Strut-and-Tie model, explain how struts behave and can be influenced by tension, and we'll look at a couple different theories here, explain how ties are designed, use the 25-degree rule near supports and loads that are applied directly to the web, and a 45-degree rule for ledged members to determine the amount of steel in vertical ties. Label different types of nodes and determine which nodes need to be designed. Develop a reasonable Strut-and-Tie model for a given geometry and loading using 7 rules for successful Strut-and-Tie modeling. Design a deep beam member using the AASHTO LRFD Strut-and-Tie method provisions, and then calculate the strength of a given deep beam using AASHTO LRFD. Typical section behavior is based on the Bernoulli hypothesis that axial strains vary linearly across the depth of a member. So this is plane sections remain plane. If we apply a moment on a typical beam, this moment will cause bending, and you can see that the vertical planes are going to remain linear. So this means in our cross section, as we're bending, we're going to bend about the geometric centroid, so we'll have 0 strain there, and then the strain will vary linearly across the depth of the section. So this is the main assumption for many of our sectional design approaches. A region of a beam is considered to be a D region, which stands for disturbed or deep beam regions, when the strains vary non-linearly across the depth of the section. Here we have the principal compression and tension stresses in a simply supported beam with a point load. You can see that in locations that are a distance D away from our supports or from our point loads, we have a non-linear strain distribution across the depth of our section. So here again, our B regions are regions where our plane sections remain plane, and our D regions are regions where plane sections do not remain plane. D regions can't be designed using design procedures that are applicable in B region designs. So our typical sectional shear analyses and design provisions aren't valid in D regions. In our D regions, we either need to design them using empirically derived expressions, or which would be specific for certain types of members, such as ledged members, or we can use the Strut-and-Tie method. And note that the Strut-and-Tie method it needs to be used in D regions, but it's also valid in B regions. D regions are caused by any abrupt changes in geometry or concentrated loads or forces, which can either be loads or support points. Here are some examples of different D regions. We have hammerhead pier caps, bent caps, both used in bridge design, ledged members, which can be used in bridges or buildings, pile caps, the cap between the pile and the column, dapped end beams, which are used to reduce the overall depth of a superstructure, coupling beams between shear walls, and walls with different openings. You can see all of these either have point loads or abrupt changes in geometry that creates our D regions. A Strut-and-Tie model is designed to simply model the flow of stresses through a structure. Essentially what we're doing is setting up a truss or kinematic model to model the stress flow through a structure. And we need to, or with the Strut-and-Tie method, we're always going to get a safe design. It's a lower bound plasticity theorem. So we're always going to get an estimated capacity that is at or below the actual capacity of the structure. And also it is a plasticity theorem, so the Strut-and-Tie method evaluates the ultimate strength of the member or structure. So it doesn't really speak to serviceability. Here we'll look at our beam, our simply supported beam with our point load again. When we apply the load, we'll get this distribution of our principal compression and tension stresses through the section. A distance d away from our supports or our load point will have D regions, and the rest of the beam will be a B region here. We can set up a simple truss made up of compression members and tension members and the points where they intersect to model the flow of stresses through the structure. So here's a Strut-and-Tie model for this beam. You can see that our compression members are dotted, and these are called struts. The tension members are solid lines here, and they're called ties. And the joint where these elements intersect is called a node. As I said, struts are the compression elements in the theoretical truss or kinematic model, and these are represented by straight dotted lines, typically blue. So here we have 3 struts in our model, and these struts will have a 3-dimensional shape that's dictated by the geometry of the member. Here we're just looking at an elevation view of the member, but there's going to be a depth to the member as well. Strut behavior is dependent on the presence of tension in the strut. And there are a couple competing theories of how that tension develops. The first theory is that the tension develops because of the spread of stresses in the strut. Within this theory, we have 2 different types of struts. One is a prismatic strut, which is a strut that has a fixed width along the entire length. In these struts, stresses can't spread, so we don't have transverse tension that develops. So we're going to have, in this theory, in this type of strut, we're going to have a higher strength for our prismatic struts. There are also bottle-shaped struts, and these struts are struts that have a wider width at the mid-length of the strut than they do at the ends of the strut. So this means that the stresses can spread, creating some tension that develops transverse to the strut axis. This idea, or the idea of these struts, or the bottle-shaped strut, originated with a researcher back in the 80s named Schleich, and he used this idea to justify the requirement for minimum strut reinforcement. So we need to provide orthogonal reinforcement across our strut to resist these tensile stresses. This theory was the basis for the ACI 318-14 strut strength coefficients, and the coefficients prior to 2014 as well. There has been some recent research, though, that has shown that there's no difference in strength between vertically oriented prismatic struts and bottle-shaped struts. So here there was research done testing struts with the same width cross-section geometry along the length, and comparing to members with wider cross-section or larger cross-sectional areas at midspan than they have at the ends of the member. So essentially prismatic versus bottle-shaped. And these researchers, Pujol et al., found that these struts have similar strengths. So it's essentially showed that maybe the difference between prismatic and bottle-shaped struts doesn't have an effect on the ultimate strength. Our second theory for how tension develops in our struts is that diagonal tension will develop in the strut because of beam bending. So here we have a typical beam, and you can see that the bending of the beam will influence the behavior of the strut. So there was research that was conducted that investigated the behavior of inclined struts between a rectangular beam where within the theory of bottle-shaped struts, stresses would be allowed to spread between support and load, and these truss-like specimen where we don't allow the stresses to spread. So there's a constant cross-section area along the whole length of the strut. And essentially, this research showed that our truss-like specimens had an increased strength compared to the rectangular beam specimens. If we can combine this with the observations from Pujol that we talked about in the last slide, we can see that there is an influence between these rectangular beams and the prismatic beams, but it is not likely because of the spread of stresses that occurs because of the bottle-shaped strut. Shown here is some testing that we did at FIU, comparing the strength of these two members, the rectangular and the truss-like specimens. Regardless of the actual mechanism and how tension actually influences the strut is controlled by, or the strut strength is determined by the area that's available at the strut to node interface. So in our design checks, we either have a separate check for this interface on the strut side, or in AASHTO, the only element that we check is our node here, and that strut to node interface. The next element that we're going to talk about in the Strut-and-Tie method are ties. So ties are our tension elements in our model, and we typically represent them by a solid line that's typically red. We need to provide reinforcement to resist the forces in our tension ties, and we also need to make sure that our reinforcement has a sufficient development length. So that means we'll often need to hook the bars or include headed reinforcement to provide sufficient development length. Also note that the center of our tie is going to be located at the center of our reinforcement. So you'll often need to assume a location for your tie in your initial model, and then after you detail your reinforcement, you may need to adjust the location of your tie. So this can be a little bit of an iterative method, or iterative procedure. It can sometimes be difficult to know what reinforcement to count for some ties. Here we have our longitudinal steel, which is obvious what steel should be counted for our tension tie here, but we have shear reinforcement along the length, so it's not as clear what shear reinforcement should be counted for our different ties. Note that this is an inverted T-beam. This type of beam is used to decrease the overall height of a structure. Beams will come in and frame into this member by sitting on the ledge, which will decrease the overall height. Within an inverted T-beam, we need to have, it's a 3D Strut-and-Tie model that can be represented as two codependent 2D strut-and-tie models. So we can have one model representing the flow forces in the ledge to get from our load point into our web, and then one model representing how we can get the members or the forces from our web down into our supports. We do need to know, though, how much reinforcement we can include in these vertical ties. So we'll have two different types of ties here. We have one tie here by our load point, which we'll call it a hanger tie, and one tie out here in our shear span, which is just a conventional vertical tie in our just rectangular section. We're going to use two different rules to determine how much reinforcement to include in some of these ties. The first is it's a 25-degree rule near supports, or if we have a load that's applied directly to a web, then we can use this rule for that as well. So with this rule, we extend a line from our support or our node over our support 25 degrees up, 25 degrees off the vertical, and see when this line intersects the top of the section. The other rule that we have is our 45-degree rule for load spreads or load spread in ledged members. We assume that our load is going to spread at a 45-degree angle. So the reinforcement that we'll include in our vertical tie is contained within this 45 degrees. So looking at our first tie here in the middle, we're going to need to use both of these rules, and we'll use these as boundaries for our vertical tie here. So our left boundary you can see in green, and our right boundary is at the edge of this 45-degree load spread. So we'll count all the stirrups contained within this region into our vertical tie. So here is our stirrup tie. And here is all the reinforcement that we're going to count in that stirrup tie. You can see that this tie is made up of 10 ties or 10 vertical reinforcement ties, and each tie has 2 legs. So we have 20 total legs of reinforcement making up this stirrup tie. We can use the 45-degree load spread rule to determine how much of the hanger reinforcement is engaged. So we're assuming that a 45-degree load spread, so we have the boundaries of our hanger tie here. So you can see that all this reinforcement contained in this region is going to make up our hanger tie. In this case, you can see that there are 7 ties contained in this hanger tie region, and each tie has 2 legs of reinforcement. So we have 14 total legs making up this hanger tie. The next element that we're going to talk about is nodes or nodal zones. Our nodes are located at the intersection of our struts and our ties, and they're named based on the types of elements that intersect the node. If we have compression elements intersecting the node, or I guess all compression elements intersecting the node, then we call this a CCC node. So all compression at the node. And this type of node is our strongest node. If we have one tension tie coming in, so here we have compression from our diagonal strut, compression from our support, and tension coming in from this horizontal tie. This is called a CCT node. So any node with only one tension tie framing it or coming into it is called a CCT node. If we have more than one tension tie coming into a node, and at least one compression component, then it's considered a CTT node. So note that we're only using 3 letters. So if we have one tension, then we have one tension here, and more than one tension element coming in, intersecting at the node, then we have 2 tension components there. And we'll use these node types in estimating the strength of our nodes. We'll also distinguish between nodes that have defined geometries and nodes that have undefined geometries. These defined geometries are typically defined by a bearing plate. So at our load point or at our load point or our support points, we'll have defined geometries. And other locations, we typically don't have defined geometries. And we'll talk about one exception in a couple slides, though. So our nodes without defined geometries are called smeared nodes, and typically we don't need to check the stresses of smeared nodes. We only need to check the stresses in nodes with defined geometries. Non-smeared nodes are going to have different geometries and features. So here's a typical non-smeared CCT node. You can see that one face is defined by the length and depth of our bearing pad. One face is defined by the height of our reinforcement. So the height of the back face is defined by, or is equal to 2 times the distance from the bottom to the centroid of our back face. And then our strut to node interface is defined by the angle of our strut and our bearing face and back face dimensions. Note that we're going to have in our non-smeared nodes, we're going to have failure at one of these faces. Shown here are the shapes of the 3 main types of non-smeared nodes. So we have the shape of a CCC node, where our top is defined by our bearing. Our back face is typically defined by the height of our compression block. So just calculating beta 1C as we would for a normal reinforced concrete member, and then using that as the height of this back face. And then again, the strut-to-tie interface defined by the angle and these 2 dimensions. We already talked about a CCT node and a CTT node. The dimensions are defined similar to a CCC node as shown here. Note that each type of node is going to behave differently, and the more tension that's in the node, the weaker it will be. So our CTT node is going to be weaker than our CCT node, which will be weaker than our CCC node. So all compression will be the strongest type of node. Nodes can also be defined as either hydrostatic or non-hydrostatic. Hydrostatic nodes have an equal pressure on all faces. So here, the ratio of all the face dimensions is the same proportion as the ratio of the forces coming into all the faces. Hydrostatic nodes don't have any shear stresses that develop inside the node. Non-hydrostatic nodes do not have an equal pressure on all the faces. So in terms of geometry, normally you'll have this kind of extra component to your node. In these nodes, shear stresses do develop. Non-hydrostatic nodes are the easiest ones to detail and lay out in your Strut-and-Tie. Hydrostatic nodes, you need to lay out your Strut-and-Tie model to get hydrostatic nodes. So they're more difficult to detail in your model. Another type of node is a curved bar node. This is a type of node that is made up of a curved bar. So here you can see compression coming in from this diagonal strut and the 2 ties coming out, and our curved bar here make up this node. In these curved bar nodes, they can fail when you have crushing of the concrete in this curved bar region. So in terms of detailing, you need to detail them so that there's a sufficient bend radius to provide enough concrete so that your concrete doesn't crush. Curved bar nodes are currently specified in ACI 318 in the Strut-and-Tie chapter 23, and you can also find some guidance provided by Gary Klein's paper on curved bar nodes. We will next talk about 7 rules for successful strut-and-tie modeling. So the first, or one of the early steps of the Strut-and-Tie method is developing a model to represent your flow of forces through or flow stresses through your structure. So there are 7 main rules that we can follow to set up a successful model. The first is that we need to enforce beam theory at our boundaries between B and D regions. In our below example here, we have a linear strain distribution at the boundary region. So we assume that we have linear strain distribution across the whole depth. So we need to make sure that our elements come in at the center of this, or of the linear strain or linear stress distribution. And we need to make sure that the force here is equal to the total force within this stress distribution here. The next thing that we can do is we can use an elastic analysis as a guide to set up our Strut-and-Tie model. So we can use a finite element software to get an elastic stress flow through the structure. And then we can try to set up our model so that our compression elements line up with compression in the model results, and tension line up with where we have tension in our elastic stress analysis. And the closer our model lines up with the stress or the elastic stress flow, the more efficient our model and our design will be. We also need to think about how practical the placement of our reinforcement will be for construction. So we want to make sure or do our best to place ties orthogonally, so at 90-degree angles. It's really difficult to construct a member with reinforcement at different angles other than 90 degrees. So while placing reinforcement at an angle may lead to a more efficient design, it's going to be very difficult to construct, and likely it'll get constructed improperly. So just in general, make sure that your reinforcement is placed orthogonally. The next thing that we need to do is make sure that our angles between our struts and our ties is greater than 25 degrees. So the angle here between our strut and our tie needs to be greater than 25 degrees. If we have an angle less than 25 degrees, the tension force from our tension tie is going to affect the behavior of our strut. So the codes will make sure that, or will limit this angle and require it to be greater than 25 degrees. Our next rule is we want to try to avoid inefficient load paths. So the load path should follow the elastic stresses as closely as possible. The model on the left, you can see it follows the elastic stress distribution that we found earlier. And we're going to have a safe design using this model and an efficient design using this model. We can come up with, any other model we want here. So this model would lead to also a safe design, but this design would not be as efficient as the design on the left. So inefficient load paths are still going to be safe for design, but they're going to lead to excessive reinforcement being used and excessive cracking. We can also split our struts to fill available space. So here, one option would be to have our loads go directly from the left and to the right support, but we can split the strut to show us where we can add some reinforcement, or where some reinforcement would be helpful. Splitting the struts is efficient and useful to a certain extent, but at some points it can get excessive and inefficient. So just using some engineering judgment here will help with this. Finally, when possible, we want to use internally and externally statically determinate systems. In other words, we want to use triangles whenever possible. It's not always possible, but we want to try to use triangles whenever possible. So here, you can see some triangles in the model, and this will just lead to a more efficient and constructible design. On the next couple slides, we're going to walk through the strut-and-tie method design process. The first step in the process is to determine any loads that are going to be applied to the member. So here we have a hammerhead pier, and you can see we had our loads are determined from the loads that are applied on our deck. So our truck and our traffic load and all the weight of our superstructure. After we know our loads, or during the same process, we can estimate our member size. We can estimate our member size by either using rules of thumb, minimum thickness requirements, past experience, geometric limitations, or given geometries for our section. So here we can estimate our column size by the given bridge layout, the width of our hammerhead pier by the given bridge layout, and the height here of our hammerhead just by rules of thumb or similar designs for these hammerhead piers. We next need to divide the member into B and D regions. Remembering that our D regions are located a distance D from any load or geometric discontinuity. So here we have a concentrated load, concentrated load, concentrated load, and a geometric discontinuity here. So our whole pier, or hammerhead pier, and column are D regions here. We'll dimension our B regions using typical sectional shear design approaches. In this case, we don't have any B regions, so our entire design will be based on our strut-and-tie method. We can use our 7 rules from before now to develop a strut-and-tie model for the D regions. Here you can see we placed some nodes under our load points and some nodes coming in from our tension element from our column and our compression block from our column, and then lined up another node here to be in line with our tension, and connected these with our different struts and our ties to come up with our model. Next, we can use either the method of sections or the method of joints from our truss analyses, or we can use a computer software to compute our strut and tie forces. So here you can see we have our loads, and using our loads we can calculate the forces in our different elements. And negative here is compression. We next need to dimension our ties with reinforcement. We can use either ACI 318 or AASHTO LRFD procedures here. And the main difference with our ties is our resistance factors. So with ACI, for struts, ties, and nodal zones, we're using a phi factor of 0.75. For AASHTO, if we're looking at compression in our strut-and-tie method, then we use a phi of 0.7. But if we're looking in tension in our strut-and-tie method for regular reinforced members, then we'll use a phi of 0.9. So you can see that AASHTO says that there's less variability and more ductility with our tension, so we can have a higher phi factor than compression. But in either case, we need to design our phi PN, so our factored or our reduced strength needs to be greater than or equal to our factored load. We'll use AASHTO LRFD for this design. So in every case, we need to make sure that our reduced strength is greater than our factored load. So our reduced strength is made up of the area of our steel times Fy for our steel. So we can solve for AS in this expression, and this is the tie force for our tie AB from our strut-and-tie model. So we can determine that our required area of steel is our force in the tie divided by our phi factor 0.9 for tension elements in the strut-and-tie method for AASHTO times 60 KSI, which is our yield strength. And we can see that there's a required steel area of 20.1 inches or square inches. Then we can determine the number of bars that we want to use. So for this design, I'm going to use 14 number 11 bars. And because there can be a load reversal, so we can have the same force in tie AB as tie CD if the truck's driving on the other side of the bridge, we're going to continue the 14 number 11 bars across the whole top of the section. This will also make it easier to construct the member. Our next step is to check all of our node stresses in our non-smear nodes. For each node, we need to make sure that our reduced strength is greater than our factored capacity, and our strength is made up of the limiting compressive stress at the node face. So this is dependent on our concrete strength and the area of each node face. And we're going to need to check the 3 different faces on each node. So we'll check our bearing face, our strut-to-tie interface, and our back face for each element. The limiting concrete stress, or F sub CU, depends on the presence of crack control reinforcement, the node type, and the face of the node. So our F sub CU equals M, which is a factor that takes into account potential confinement effects, V or nu, which is dependent on whether we have crack control reinforcement and the type of node and the face, and then our F prime C. So for structures without minimum crack control reinforcement, our nu is equal to 0.45. If we have minimum crack control reinforcement, this nu value is dependent on if we have a CCC node, a CCT node, or a CTT node, and dependent on the face. So for the strut-to-tie interface, we have an equation to calculate the factor, and it's this equation is bound by 0.45 and 0.65. Our back faces for our CCC node are defined as always 0.85, and for our CCT node 0.7, and then in our CTT node we use this equation to calculate the factor on all the faces. And again, it's bound by 0.45 and 0.65. So you can see these factors will reduce the strength of our concrete that we can consider in the strength of the node. And our CTT node is going to have the most impact, so the lowest factor on all the faces. We also have a factor called the confinement modification factor, M, which takes into account the confinement benefits that you can get if your bearing area is smaller than the member that's being loaded. So you can see here our A1 is the area under our bearing device, so shown here, and our section you can see that's being loaded is larger than this bearing area in this figure. So our A2 is called the notional area, and this is the area if we extend out a line with a slope of 2 to 1 here. When this line intersects the edge of our section, that's the plane where we'll measure our A2. So here our plane intersects or hits this left boundary first. So this will be the left edge, and then we can extend out a 45-degree angle to get our top boundary, and then we'll have an equal width here as we do here on the left to get this right boundary, and the bottom is the same as the top. So then our M factor is just equal to our A2, or our square root of A2 divided by A1 less than or equal to 2. So you can see that if your bearing is much smaller than the area that's being loaded, your F sub CU can be as large as 2 times the value if you didn't take into account confinement effects. So it can have a large impact on your strength. The minimum strut reinforcement in AASHTO is broken up into vertical shear reinforcement and horizontal shear reinforcement. So you need to provide more than 0.003 reinforcement ratio for vertical shear and horizontal shear. In thin members, you can just get away with having 2 legs of reinforcement. But if you have thicker members, then you need to distribute the reinforcement across the cross-section width. And note that the spacing of these grids is also limited so that it can't exceed the smaller of d/4 and 12 inches. So those are the minimum spacing requirements for our vertical and horizontal shear reinforcement. While AASHTO only requires checking node stresses, ACI also requires checking the strut capacities. You can see here we have different equations for our struts with and without longitudinal reinforcement, and also different equations for our node capacities. Our struts and nodes, we both have an effective concrete strength where we have a beta S factor for our strut capacity and a beta N factor for our nodes. We also have a beta C factor that takes into account the confinement benefits of having a bearing smaller than the member being loaded. This factor is similar to the factor that we used with AASHTO. The beta C and beta S values are shown on this slide. Beta C factor is found the same way as AASHTO based on our A2 and A1 areas. The beta S factor depends on the strut location, whether we're in a tension member or in another case in compression or flexure. Our strut type, whether we have a boundary strut or interior strut, so interior or boundary strut, and also our criteria, which is mainly if we have minimum strut reinforcement or we don't have minimum strut reinforcement. Although there are some other locations and types of connections where we can also use beta S of 0.75. The beta N factor for nodes are shown on this slide. These factors depend on the forces coming into the nodes. In other words, the node type. If we have all compression, we have our highest beta N of 1.0. As we start introducing tension, this decreases our beta N value. So a CCT node with 1 tension element has a beta N of 0.8, and a CTT node with 2 tension elements coming in has a beta N of 0.6. ACI 318 has an additional check to ensure that a diagonal tension failure, shown here, doesn't control. For this check, our ultimate factored shear needs to be less than the value found using this equation here. If the equation controls, then you either need to increase your concrete strength, your BW, or your D. More details on this check can be found in Klein et al.'s paper, Shear and Discontinuity Regions. In ACI 318, minimum strut reinforcement can either be provided in an orthogonal grid, shown here, or in one direction, shown here. So depending on whether you're providing the reinforcement in both horizontal and vertical directions, you need to either satisfy this equation here, this ratio in each direction, or in one direction, we can satisfy this equation here. The angle alpha 1 depends on the angle of the reinforcement to the strut angle. So here we have our vertical reinforcement and our diagonal strut, so we can find our angle alpha 1 as shown here. Other requirements for the minimum strut reinforcement are shown on this slide. The spacing of the reinforcement shall not exceed 12 inches. So your spacing of these vertical bars, or in the horizontal case, they need to be less than 12 inches. Also, our angle alpha 1 needs to be less than 40 degrees. So this angle here needs to be less than 40 degrees. The designer needs to check all the faces in our nodes with defined geometries. So in this case, we're going to check all the stresses in nodes A and D, which are CCT nodes, and node E, which is a CCC node. The other nodes either have smeared geometries or will not control by inspection, so we'll ignore those. So we'll need to check all the faces of our different nodes. We'll use AASHTO LRFD provisions. and we're going to assume that we have a confinement modification factor just equal to 1. So we'll ignore the effects of the benefits of confinement for now. You can see node A is a CCT node. So we'll use these factors for new. And if we're looking at our strut to node interface, then our new is equal to 0.85 minus 5 KSI, which is the strength of our concrete, divided by 20 KSI, which is equal to 0.6. And our 0.6 falls within our range of 0.45 to 0.65, so we're okay using that. We can use this and our assumed M equal to 1 to find our F sub CU, then calculate our width of our strut to node interface or using this expression from geometry, where 30 inches is our bearing length and 13 inches is the height of our back face, and 32.9 is the angle of our strut. And then with this length of our strut to node interface, we can calculate the area of this interface, take it times the F sub CU, the effective concrete strength, and then times our phi factor for compression elements in our strut and tie model, and calculate our factored strength, which is equal to 2,056 kips in this case. We can then compare this to the force that's coming in at this node and make sure that our phi PN at the strut to node interface is greater than the force that's applied at this face. So we're okay with this node. We can do the same thing with our bearing face and our back face and make sure that our factored capacity at the bearing face is greater than the demand on that face, and the factored capacity on our back face is greater than the demand on that face. So in both cases, we're okay. So then we know that our node A is okay. We can then do the same checks for our node E. In an actual design, you need to check the stresses on all your nodes. For this example, we're going to assume that all the other nodes or the stresses check in all the other nodes, just for simplicity. So the next thing that we need to do is proportion our crack control reinforcement. Using AASHTO LRFD, we need to ensure sufficient vertical and horizontal shear reinforcement. Since this is a wide member, we're going to distribute the reinforcement with 4 legs across the cross-section. For the vertical reinforcement, we'll try using number 5 bars spaced at 7 inches on center across the cross-section width, with 4 legs across the cross-section width. So we have 4 number 5 bars divided by 54 inches our BW, and divided by 7, which is our spacing, which we can see we have a sufficient reinforcement ratio here. With our horizontal shear reinforcement, we're going to try using 9 number 5 bars spaced across the height of our section and located in 4 planes across the cross section. So we have 4 planes, 9 bars, number 5 bars, and then divided by 54 RBW, and then divided by here 55, which is the average height of the beam. And we can see that we have sufficient reinforcement provided in the horizontal direction. We'll next need to check our tie anchorage requirements. And to do this, we need to determine our required development length. And we're going to use the AASHTO development length equation for hooked bars, shown here. So for this expression, we have a couple modification factors, and then we have this L sub HB. So solving for L sub HB for our number 11 bar with our 60 KSI yield strength and 5 KSI concrete, we can find that the required, or the L sub HB here is 24 inches. Our reinforcement is not epoxy coated, and we're using normal weight concrete. So we're going to assume that and also we're going to assume that we can't take advantage of any other reductions, just conservatively. So our development length will be equal to 24 inches. We can compare this then with our available development length. And our available development length is from the back of our hook to the point where our reinforcement leaves our extended nodal zone. So for us, we have 13 inches being the distance from the back of the hook to the edge of the bearing. 30 inches is the bearing length. And then 3.3 inches divided by the tangent of 31 is 31 degrees is this extra distance that it takes for the reinforcement to leave the extended nodal zone. So you can see that our available development length is 48.5 inches, and this is greater than our required development length for the hook of 24 inches. So we know we have sufficient development length for our hooked bars here. Our next step, which is an optional step, is we can optimize our Strut-and-Tie model to make our design more efficient. So if we change our model, then we need to go back to step 5 and redesign our reinforcement and recheck all of our nodes. So we would cycle back through. Otherwise, if we're content with our design, then our design is finalized for strength. The last thing that we can do would be to check our serviceability under service loads. So if we calculate our VC component for using either ACI or AASHTO LRFD expressions, our section, if it's a kind of a normal beam section or something like that, it will normally crack at around a shear equal to the V sub C component of our sectional shear strength. So we can then compare our service shear to the concrete component of our sectional shear strength and make sure that our service shear is below that. And that will normally ensure that our structure doesn't have shear cracking. On the next couple slides, I have some examples for Strut-and-Tie models. So if you want a challenge, then pause the video before I click on to the next slide so that you can try to develop your own model. So here we're going to look at adapt end beam and a wall with openings. And you can see we have different loadings in each. The first thing that you can do to help with your model is try to locate where you want your nodes to be. Normally nodes will be under load points or above supports. And another common location is in corners or around corners where you think you might want tension reinforcement. So in a adapt end beam, we know we're going to get some tension here in this corner. So I want some nodes right around the corner. Same thing with the wall with openings around some of these openings. We'll want some nodes. So if you want to try to lay out your Strut-and-Tie model, then pause the video here. Here you can see a common Strut-and-Tie model for the adapt end beam, and then also the wall with openings. And if you had developed a model, then you can compare these with what you had developed. You can notice that I tried to lay out all of our ties to be either vertical or horizontal, and this will help with reinforcement placement. And you can also see that we normally want some reinforcement around our openings, so trying to lay out the model so that we have some reinforcement around the openings will help with the behavior. The next model we'll develop is for a deep beam with 2-point loads. So again, if you want to try to develop your own model, then pause the video here. The first thing that we can do is lay out the location of our nodes. So we can put some nodes above our supports, under our loads, and then we'll put some here in this longer span. And here we can connect those nodes and develop our strut-and-tie model with um, our tension ties being either vertical or horizontal here for easier constructability. Next, we have an awkward wall with an opening in the middle, with a point load on top of the wall. So you can pause it if you want to try to develop your own model. First, we lay out the location of our nodes. So you can see here some of the nodes that I placed. And then we can connect those nodes with our different elements to get our model, trying to get some steel around our window opening here and at the bottom of our member. We're next going to look at an example problem. And this example problem goes along with some testing that I did at the University of Texas. So this is these are inverted T-beams that we tested with different shear span to depth ratios. So normally for each beam, we would get 2 tests out of it. So one test would be run with an A/D of 2.5. We'd add some external post-tensioning or kind of clamp down on the section to add additional shear reinforcement to strengthen this side, and then fail the other side with a shorter shear span. So you can see that the failure is it's a pretty brittle failure, and this is typical for deep beam sections.
It's unloading.
Unloading? Yes. Keep loading a little more. How much is it down?
It went to 913, it's 902.
Yeah, let it go down like 800. Let it go down to 800.
So on the left, we had a more brittle failure, and this was controlled by crushing at one of our nodes. On the right, with our larger shear span, we had failure of a tie here. So the tie, or failure of a tie means that we have failure of our reinforcement. So you can see it was a much more ductile failure than our failure on the right here, or on the left. Shown here are some of the details for these sections. So these were inverted T-beams. We had 3 point loads that we applied on the ledges of the members, and we had simply supports at the ends. And again, we had a shear span to depth ratio of 1.85 on one side and 2.5 on the other. We'd test and fail one side of the beam, add some reinforcements, external reinforcement to increase the capacity of that tie, and then fail the other side of the beam. You can see the cross-section details and the details for our vertical and horizontal shear reinforcement here. The section properties and material properties for these specimens is shown on this slide. You can go now to the video for example problem 1. Shown on this slide are some resources for additional study on this topic. And this concludes our presentation.